This is the beginning of my note recording palooza. I hope you enjoy and join me. I have this loose shape out here. This is just that level curve, that topographical map of a 3D shape, where each one of these is like the shape at a different height. This would be when f of x equals 12, or height equals 12. This would be when f of x y equals 11, f of x y equals 10. And then we have this other idea coming in where I have a constrainment. I have another function that comes in and says, hey, well, it's restricted by this. We saw this out here. I wanted to know when my volume function was restricted by my surface area function, and those two restrictions interacted in such a way. So I have another curve coming in from another function, and it intersects. Boom. But it doesn't just intersect. It's not a simple intersection. I'm going to call this second curve g of xy. And that intersection is a very special moment. And guess what? At this moment, these two things share a tangent direction. I'm trying to lock the focus here. They share a tangent direction. And we know it makes a right angle with both of these at that moment because they share that constraint. They share that moment in time, and they're going to share a derivative. They're going to share a gradient vector, but they're not perfectly the same. There's a multiplier here. This is my Lagrange multiplier. That is the Greek letter lambda, where because these vectors are parallel, they're going to be able to be represented as a scalar multiplier of one to the other. And I could just as easily move this to either side if it made an example easier. But yeah, this is where my del f is, and my del g would be the exact same place, except it would just be multiplied. Same direction, different magnitude, because it's a slightly different function. And so you could manipulate this equation, even something like this, minus. It is possible, but really, we have two parallel gradients at this moment, and I can leverage one gradient against the other gradient and come out with some great stuff. Let's do some examples. We are going to use this to do some critical value tables, some EVT, some absolute mins and absolute maxes, where I can have a function and find its maximum given a specific constraint in a specific area, kind of a thing. Let's do it. Same exact problem, same exact idea. I'm going to have a box. This box is going to have a lid where I'm going to call this my volume equation. Looks like this, length, width, height. Why won't this thing focus? It's really struggling to stay in focus, and the camera just keeps moving. Let me zoom out. Zoom in. And autofocus. Alright, I'm hoping that's going to be okay, and it's going to stop snapping, because I can see it out of the corner of my eye. It's driving me crazy. I'm sure it's driving you crazy. Okay, over here, I'm going to, I could call this f of length, width, height. I'm going to call my second function g of length, width, height. That's equal to the surface area. That's equal to 2 length width plus 2 length height plus 2 width height. And so what this is saying is, hey, these partial derivatives should be equal to each other. Remember, when I do the gradient, the partial derivative with respect to x is completely independent of y and z. That's why it's a partial. So I'm going to do this. Partial derivative of my volume equation, width, height. Partial derivative, that should be a little L. Of this guy as well. That's 24. I forgot to write that one. 2 width plus 2 height. Well, I know that we're looking for a moment where these two gradients are the same. We're looking for a place that the box's volume is constrained by this g function, this other curve swooping in and running into this volume function. Well, that just means that WH is equal to 2W plus 2H times this lambda is what we're going to be solving for. In this case, I'm going to just move it over and say, hey, lambda is equal to WH over 2W plus 2H. I don't have enough information in this moment. 2 variables, 1 equation. So I'm probably just going to have to jump over and do the same thing with width. Well, the issue with width is I'm going to see the same thing. And so I know that length height is 2L plus 2H times lambda. That's same lambda, that's same value. And so lambda would also equal length times height over 2 length plus 2 height. Well, if I know these are both, well, let's do all 3 dimensions. Before I get too far ahead of myself, let's do all 3 dimensions. But guess what? We're going to say the same thing with height. Length width, 2 length plus 2 width. Therefore, this is true times lambda. Therefore, lambda equals length width divided by 2 length plus 2 width. And when I kind of lay these all next to each other, lambda is equal to WH, 2W plus 2H, LH, 2L plus 2H, LW, 2L plus 2W. You start to recognize that, well, if I just look at the first two, the only way this numerator is equal to this numerator is if length is equal to width. The only way this denominator is equal to this denominator is if length is equal to width. And that same logic would carry over here. This implies length equals width equals height. Well, if length equals width equals height, I hop back up to my surface area. I'm going to just call this the side. 2 side squared plus 2 side squared plus 2 side squared. That means 24 is 6 side squared. That means 4 is side squared. That means my side is 2. Well, then I know that length equals 2, width equals 2, height equals 2, and all this culminates in volume being 8. Much quicker, much more succinct than the previous version. And this will hold true for all sorts of different things. This concept of, hey, if I have this function and this constraint, so I have this parabolic thing where z versus x is a parabola, z versus y is a steeper parabola, and I'm slicing it on this circle, x squared plus y squared equals 1. I have this cylinder cutting through. Where am I going to find the highest heights? Or the lowest heights, the lowest and highest z outputs inside this region? You can use a little logic and find it, but again, what I'm going to do is I'm going to take f sub x and set it equal to g sub x times that lambda value. Well, f sub x is just the partial with respect to x is 2x. G sub x is the partial with respect to x, which is just 2x. And so here we have this thing where 2x equals 2x times, and I'm going to just keep trying to make it more obvious that that's not an x. That's lambda. And the only way this is possible, if 2 times x is equal to this, the only way this is possible is if lambda equals 0 or 1. All right? Well, if lambda equals 0 or 1, let's look at the y values as well. I do my y partial derivatives. Here I get 4y. G sub y, I get 2y. And so I know that if 4y equals 2y times lambda, I kind of have my two cases. Right. If lambda equals 1, then 4y equals 2y, then y equals 0. Well, if y equals 0, then I can plug it into my constraint. Oh man, I'm way off the page. If I know y equals 0, I can plug it into my constraint. This is an equation that's solved. This is a function, this is a mystery. This equation is solved. So if I know that lambda equals 1, y equals 0, that means x squared plus 0 equals 1. That means x equals plus or minus 1. So that's taking care of my lambda equals 0 case. What if I went back up to my lambda equals 1 case? What if I went back up and checked out my lambda equals 0 case? I know that if lambda equals 0, oh man, why would I do that? Either lambda equals 1 or x equals 0. Duh. That was my issue. I misread my own notes. Go back. I apologize for that. That's why I only cared about the lambda equals 1 case down here and was ignoring the lambda equals... I just feel like an idiot. Because if lambda equals 0, it's kind of senseless. It means that that works in every case. Actually, it would work in no case. If I multiplied this vector by 0, I would not get this vector back ever. That doesn't make any sense. And that means this side would be equal to 0. Yeah, it's just bad logic. So now let's take this x equals 0 case over here, where I have if x equals 0, then I know that y squared equals 1. That means y equals plus or minus 1. And so now I have all these coordinates coming out. And I build a nice little candidates table out of this thing. I have my coordinates from down here, my 1, 0, and my negative 1, 0. I have my coordinates from up here, 0, 1, and 0, negative 1. And I'll plug those into my f of x function. And I'll get my mins and maxes. Those are my extreme values. And I didn't find them from a second derivative because my issue is that I'm restricted on this domain. And so I want to find those restrictions or intersections just like we did way back in Algebra 1. Let's hop over to Desmos and show this to you. So here are my functions in Desmos 3D, and I can kind of see them here. I see my elliptic paraboloid, and I see my cylinder, and there's their intersection. I could see this kind of potato chippy, wavy thing happening from my mins and maxes. I see they happen on the intersection because inside, like I do get this minimum 0, 0, 0, but it's not within this restriction. And that's why I'm only looking at the intersection. And basically, by setting those partial derivatives equal to each other, I'm testing every moment along this ridge to find where my mins and maxes are. Even if they're a little bit obvious to us that we're going to find some here, and here, and here, and here at the poles, it's still, as my functions get more complicated, as our situations get different, we would continue to see that happening. I'm already gone 12 minutes. We gotta get moving on this backside. I see this extreme value of this closest me issues, not because I was incapable of doing it, just because it's a good bit of work, folks. It is a good bit of work to get this done. So let's stick together. I know we're gonna see this through because we're again going to abuse that distance formula. Distance would be x minus 3 squared plus y minus 1 squared plus z plus 1 squared. And so I know my g of x, y, z is going to be d squared, is going to be x minus 3 squared, y minus 1 squared, z plus 1 squared, just like we did in the last set of notes. That's just a nice way to kind of abuse our distance formula to make a multivariate function that I can now use as a constraint for this. I can now use this as a constraint for this multivariate function. And the reason I'm going to use this one as the constraint, I mean, again, I can kind of flip that lambda. It'll work either direction with this as my f and this is my g, or this is my g and this is my f. It really works either way. But I know that I'm going to be leveraging this one more heavily because it has an equal sign. And so as I'm getting my x and y values, I'm going to be plugging them in here to leverage it to get the other value that's missing. If I get x, I can find yz. If I get xy, I can go find z and relate it all to 4. All right, so let's do some partial derivatives. Are you ready? I'm going to move this back just a tiny bit. Doesn't feel like my lights are very bright. Maybe it's just my laptop angle. Yeah, it's the laptop angle. Here we go. I'm calling this guy f x, y, z in case you didn't know that. So when I do f sub x, it makes sense that it's 2x. And when I do f or g sub x, I get something slightly different. But g sub x, I'm going to get 2x minus 3 with a little bit of chain rule. And again, so what this says is 2x will be equal to 2x minus 6 all times that multiplier lambda. That constraint, that stretch lambda, that scalar that'll make my two vectors equal to each other. Don't look ahead. That's scary stuff down there. All right, so over here, I'm going to divide everything by 2. Still times lambda. I could even distribute this lambda. X equals x, or lambda times x minus 3 lambda. I want to solve for x because I want to start substituting it in other places. So here I'm going to get x minus lambda x equals negative 3 lambda. And I'm going to factor out that x, 1 minus lambda. I get negative 3 lambda over 1 minus lambda. That's what x is equal to. When this is maximized, when I find the extreme values, it's going to happen here. All right. I'm going to see a very similar pattern when I get to the y values. All right. F sub y is 2y. G sub y is going to be 2 times y minus 1. And so I'm going to see a very similar pattern come out with my lambda when I set this equal. I hope you trust me and believe my little bit of algebra to save you a little bit of heartache as we make this jump to say that y equals lambda over 1 minus lambda. I'm going to use those same algebra steps here as I did there. I'm going to divide out the 2. I'm going to move the y lambda over. I'm going to factor out the y. I'm going to divide. All right. And actually, honestly, the same thing with z. F sub z is going to be equal to g sub z times lambda. This one's just a little bit different. No, it's not. It's exactly the same. I'm taking crazy pills. I made a... No, I did make a mistake. I think I just made a mistake in my notes that I'm looking off of. Don't mind me losing my mind. Again, we're going to go through the same process. I mean, I guess I could show it that 2z equals 2 times z plus 1 times lambda. But I promise, all it's going to flip is this little sign. You know, kind of comparing these two is that my sign flips. And that up here I'm going to get z equals negative 1 lambda over 1 minus lambda. So the only difference between these guys is the negative. And so that's why I see that. Now, we're going to plug all of these into my constraint. I have x, y, and z all in terms of that lambda. And now I can make that big substitution in here and solve for that missing lambda. So I've got negative 3 lambda, 1 minus lambda squared. Lambda over 1 minus lambda squared. Negative lambda, 1 minus lambda squared equals 4. And would you believe it, this is totally a solvable rational equation, right? I'm going to get 9 lambda squared, 1 lambda squared, 1 lambda squared. That's going to make 11 lambda squared on this side. I'm going to multiply over by this denominator. So this would be 4, 1 minus lambda squared. I hope you trust me to be able to do that. Skipping a little bit of algebra there for the sake of space and time. All right. 4 minus 8 lambda plus 4 lambda squared. Absolutely. I'm going to move everything over. 7 lambda squared plus 8 lambda minus 4 equals 0. And what this gives me is that lambda equals negative 4 plus or minus 2 rad 11 over 7. Quadratic formula there with the small simplification dividing everything by 2. Alright, I know I'm breezing through the algebra, but I know you know how to solve a quadratic. And honestly, I know this looks extra yucky. There are some simpler problems out there. Like, this is definitely the simpler version. This is an applied version. This is the hard version. So understand, this is as hard as it gets. I cannot do any more except for the next example, which in some ways will look harder, but also in some ways will look a little bit easier, honestly. So now that I know this lambda value, I can just go plug it in to x and y and z. X and y and z. So when I do that, I will get these values. My first coordinate when I plug in the x, y, z is going to be 6 over rad 11. Again, all I'm doing is taking this in, plugging it over here, 3 times lambda over 1 minus lambda, and simplifying. 2 over rad 11. Negative 2 over rad 11. When I plug in the minus version, right, this is a plus or minus. Negative 6 over rad 11. Negative 2 over rad 11. Positive 2 over rad 11. And so now this is my opportunity to find out which is the min distance, which is the max distance from that 3, 1, negative 1. I see that this is positive. It's going to be close, positive, close, negative, close, where these have opposite signs. So they're going to be farther away. This is my closest, or my min distance. This is going to be my furthest, or my max distance. Again, just to recap, I need to build 2 functions so I can set their partials equal to each other times some scalar multiple. So I made a distance function of x, y, z. I had my sphere actually, and compared the sphere to that distance formula and said, hey, when is the partial of my sphere equal to the partial of my derivative? The partial, 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 partial. And I got this back in, kind of leveraging that system of equations, because I eventually had 3 variables in 3 equations, and I was able to solve it. Woo! A little bit easier on this one because we just can't make the questions that difficult. If I had multiple constraints, right? If I had a minimum of this function on the intersection of this plane and this cylinder. So I'm looking at the intersections of these and trying to maximize the output of this guy. So I'll find some critical values where all 3 of these things interact. I'll plug them in here and find out which one is the min and which one is the max. Okay. Because these are nicer, I'm actually just going to write out the derivatives in this way. Like, again, lambda del g plus mu del h. Just to show it this next, my derivative here is 1, 2, 3. My derivative here is 1, negative 1, 1. My derivative here is 2x, 2y, 0. And now I set up all 3 individual equations for my partial x's, my partial y's, and my partial z's. 1 equals 1 lambda plus 2x mu. 2 equals negative 1 lambda plus 2y mu. And the last 3 equals 1 lambda and no mu. So I know that lambda equals 3, and now I can keep working backwards and kind of leveraging that to maybe solve for a little bit of x and y. Okay, so here we go. If I know that lambda equals 3, I know that 2 equals negative 3 plus 2y mu. I wrote that mu very ugly. And I use just my little bit of algebra, add the 3, divide by the 2 mu. I get y is equal to 5 over 2 mu. Again, I'm not quite solved. Again, here I would get the equation 1 equals 3 plus 2x mu. Minus the 3 is negative 2. Divide by the 2 mu. The 2's cancel out, and I'm left with this guy. So now, again, we're just leveraging systems of equations and just trying to solve for these various things. Your best guess is to at least build this and look if you can solve one or pick one off. Now I'm looking for, just as we did in the previous problems, some common thing to then relate them across. Here I had x, y, z equals a constant. Here I'm looking for x and y equals a constant, and so I get my circle here. Where x squared plus y squared equals 1, I would get negative 1 over mu squared plus 5 over 2 mu squared equals 1. And now I'm just algebraing to solve for mu, because once I get mu, I can plug it back into x and y. I'll have x and y. I can go find z once I have x and y, and then I'll have the cases where to min and max, because I'll have the list of all of my min and max x, y, and z values. Here we go. Okay, so that's going to be 1 over mu squared plus 25 over 4 mu squared equals 1. Multiply both sides by that 4 mu squared. So if I multiply everything by 4 mu squared, over here it would just make 4. Over here it would leave the 25. On this side, 4 mu squared. And so when I add these, divide, square root, I get rad 29 over 2 is mu. Now, I go plug this in. You know, I'm just trying to block off so you can see where my work's going. If x equals negative 1 over mu, the reciprocal. Oh man, did I do all that work off page? That's lame. If x equals the negative reciprocal, that means I just need to make this the negative reciprocal. Oh, but I forgot square root, plus or minus. So if this is plus or minus, I don't know if you've seen this symbol before, but because this is negative, this is going to be equal to minus plus square root 29 over 2. Because it's going to be the flipped symbols from what this gets plugged in. So now when I go to plug in my y values, and I'm plugging this in, and it's getting reciprocated, and a 2 is going to cancel with a 2, y is going to be plus or minus. Because there's no negative to negate this symbol stays plus or minus 5 over rad 29. I wrote this backwards, didn't I? I forgot to reciprocate it. I think I'm losing my mind today. Minus plus 2 over rad 29. Last but not least, I have to go find my z value using this x and this y. Well, thankfully, I have this up here, where I know z equals 1 minus x plus y. And so I'm just going to plug those in. I'm going to get plus or minus. I'm going to get 2 values out of this, and we'll see how it works. The first one, I use the minus and the plus. I have to use the top symbol because when mu is equal to the positive, I would get the negative positive out of this. Negative negative makes a positive. And when I go plug in that negative, 1 minus the x value, sorry, I brain fart, minus the y value. Shocker. I get a plus minus. All right. I know that I'm dragging you along to get here. I promise we're going to find the constraint. We are 1 moment away. It is all systems of equations. If you felt good about systems of equations, you should feel good about this, because I'm leveraging this system to solve this system, to solve this system, to now go check what my max and min values are. Again, my master function, the one I'm trying to maximize, is x plus 2y plus 3z. I'm going to plug in my x my y, and my z. And again, in case 1, my x is going to be the negative. My y is going to be the positive. And my z is going to be the positive. When I plug that in up here, I'm going to get -2 plus 10 plus 21. Oh, I dropped 1 plus. So I'm just going to write it out. -2 over rad 29 plus 2 times 5 over rad 29 plus 3 times 1 plus 7 over rad 29. If you can imagine, the rad 29s are all going to be common terms here, and I'm going to get 3 plus, that'd be 10, 21 is 31, minus 2 is 29. To simplify this way. Case 2 is going to be the same, but I'm going to have all my signs flipped from the minus plus and the plus minus. And again, I'm going to plug them in the same way. 2 over rad 29 plus 2 times -5 over rad 29 plus 3, 1 minus 7 over rad 29. And when I simplify this one out, I do get out of my function output here ends up being 3 minus, it's going to be 2 minus 10 minus 21 is that same kind of concept. Those plus minuses really help us out here. And again, I'm looking to label max and min outputs. That's a max. That's a min. So by taking the partial derivatives and setting those partial derivatives equal to each other, I find these special moments where they share that gradient. And when they share the gradient, that's where those min and max points are found, because the mins and maxes are found based on the intersections of a constraint and the original function, or multiple constraints and the original function. Then, once I find those intersections and those special moments, I go test them against the original function and classify outputs as mins and maxes. As simple as this, as complicated as that last one. Have a great day.